Welcome to lecture number 10 of the Mathematics and Statistics of Infectious Disease Outbreaks. Today we will be talking about multivariate outbreak detection, and I will choose the following agenda for this. I will talk a bit about using univariate methods in parallel to achieve this job, and then I will talk about the Kuldorff scan statistics, and I will conclude by showing and illustrating a case study where you will see this put into action by analyzing meningococcal data, disease data in Germany with the Kuldorff scan statistics. And the material I'm covering is based on a book chapter I wrote together with Benjamin Alevius, and it's linked from the homepage. So you can follow the material also from the univariate detection by looking at that chapter. So let's look at the setup for multivariate outbreak detection. So in the last lecture, in lecture 9, we looked at a univariate time series of count, where yt is the random variable describing the number of counts in a particular time epoch. And typically that could be weekly data, but it could also be daily data, monthly data, yearly data, depending on the time scale and what you're analyzing. And so there will be some time point 1, and there you will start the observation, and then this will go forward in whatever time unit you're defining, but it's in discrete time. And so far we looked at yt being a univariate character. That means it's measured as a scalar, and in particular we looked at it being counts, or at least something which were counts, but then we later also approximated to be continuous. But so far we will always say this is public health surveillance, or this will be discrete entities we will be looking at, and in particular cases or a number of individuals. So yt will be a discrete random variable, but it will be univariate. That means it is one-dimensional. And so the extension in this part of the lecture is that we're going to say that, well, yt is not going to be scalar anymore, so one-dimensional, but it will be instead be p-dimensional. So that means one observation yt, and I will denote this by a bold yt to denote that it's not univariate but multivariate, will consist of yt and then the first component, second component, blah, 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 until the pth component. So this will be a vector of length p. And this is just out of convenience. I will write this as a column vector, but it doesn't really matter if it's column or row, as long as you're consistent in what you write up. So what is the difference between, so maybe first thing is if p is equal to 1, then of course we have the special case we already know, then we have the univariate time series. So why do we really want to bother about these p-dimensional? Well, it could represent different things, and we will still say that each yti, so each of the components, will still be an count, a number of cases, new cases, which were observed in a particular week, for example, or the number of reported cases in a given time point. And now, why do we have P suddenly? Well, it could be that we're looking at regions. That could be the lane in Sweden. It could be different countries around the world. It could be different cities, whatever. And that's at least the most common, because, and then you can talk about that some of them are closer to each other than others, and then of course interesting things happen and you want to maybe take that into account. But it doesn't have to be region. It could also be age groups. You could have that you have, like we had in the mortality monitoring data, that you have, I think it was 8 age groups. So you divide somehow arbitrarily the individuals into 8 age groups, and then you monitor what's going on in these age groups. It could also be gender, male, females, but it could also be, for example, different serotypes of a disease, like you saw with salmonella. There are different serotypes, and maybe you want to monitor them all in jointly, or even at a higher level, it could be different pathogens, or maybe some symptoms which are related to a particular pathogen. And it doesn't necessarily have to be one of them. It could also be that it's a combination of age and gender, or maybe of region and age. All kinds of things imaginable, but the most common, and that's the one which will be of interest for us is that these are different geographical regions. So that could be Kommune or Län in Sweden, counties in Germany, for example. It doesn't sort of like whatever you can imagine it could be. It's just a choice that the recording of cases also follows some spatial aggregational level at which these are reported. And of course, diseases don't care much about geographical borders, but what does care about it is the way data are reported. So that would be maybe a typical thing. That is geographical region. And the aim is now to monitor these P time series. So you could think of each component here, YT1, as a time series by itself. So the marginal time series of the first component, that would be one time series. You have the marginal time series of the second component and up to the peak component. So you have P joint P time series that you could either think of as being in the sort of like independent of each other, but what the idea is now to try to at least monitor them simultaneously. And the hope is, of course, that you can gain strength by this joint approach, that you can, for example, detect very weak signals if they're scattered in all 10 regions that you're looking at. You have a small increase, but it's consistently in all 10 regions simultaneously. Then maybe you can gain something from that. Or if it's 10 region and in 5 of them you have this small but increase, but they are geographically connected, that could be there could be an explanation for that. And that's the hope of the multivariate detection, that you gain strength, in particular in connection with spatial phenomena. You often use that. So which ways, and we will talk about only 2 methods to look at this multivariate outbreak detection or multivariate monitoring. And the first and simple ones that you already have seen is simply to, if you have a p-dimensional time series, but basically the marginal components are that you have corresponds to that you have p time series, well, let's monitor with method that you learned in lecture 9 each of these time series. So this is a very simple method, is to multiple these different data streams. I will call them multiple time series or more simply multivariate time series, is to simply use a univariate method on each of these time series. So that's of course very easy because you know already how to do that. And this is the nice thing, is this scales linearly, right? You don't need sort of like extra big computational power because things become more complicated. You simply do it for each component, so you have an increase by linearly in the number of components. And of course, you would then get alarms for each of the individual time series. And then you can think about, is there a smart way to combine these? You can really do some rough rules of thumb. Say you have 10 regions. If you have alarm in 4 of them, then you're going to do something in particular. Then you can play around with the alpha, how much or how little you want to do there. And so on. So you can think about sort of like there are easy ways and rules of thumb, you can say, to combine these. If there's at least one region which has an alarm, then you're going to want to react, or so on and so on. On the downside is that, of course, and I already touched that, is that the false positive probability. So the probability to get a false positive is alpha at each time per series. But since you're monitoring p time series jointly, it's gonna be the probability that you will get an error overall, at least one error, for your time series, depending on, of course, how you aggregate, but let's go on the lower level. So to get at least one alarm, if that's your rule, to flag the entire time slot for an alarm, then of course that probability will be way higher than alpha, because you have, let's say, 10 time series you're looking at jointly. Then of course the false error probability is higher than for one. Easily shown, easiest to show on the independence, then it's simply the probability to get more than one alarm by the binomial distribution. If they are independent, of course, that's the thing, is they might not be that. So of course, then the probability is a different one. And then you can think about, okay, well, there are all kinds of ways to adjust for such multiple testing problem. 10 regions. We can do a Bonferroni. We just take our alpha and divide by 10, and then we use the smaller alpha. But of course, if you use a smaller alpha for each of the time series, then of course also outbreaks are harder to detect because you need more significance, or not more significance, you need more evidence to before you react. So of course, this is something you may want to think about. And you already saw such an example in lecture 9 that we have all these Salmonella serovars, and as I just said, each row is the univariate monitoring, and there was no combination of results here. So here's another example, which is something we worked with a while ago with the correspondent to the Smitskydsinstitutet or Folkhälsomyndigheten for humans. There's also something like that, the Friedrich Löffler Institute in Germany, which is responsible for animal health. So here, this was an example from infectious diseases among animals, and it's in particular it's rabies in foxes, which here is of interest. And what we did here, we have all the counties in the federal state of Hesse, which was one of the federal states having a problem here. So here, each of these are the so-called identity numbers of the individual counties, Kreise in German. And I divided them in 3 regions. There's a north region, a middle region, and a south region, which are also happen to be administrative, so-called Regierungsbezirke in German. Maybe, yeah, I'm not sure what, I don't think you have this middle level, and it's not really used that often. And then I have here the total for the federal state of Hesse. So you see here the individual time series. You see the blue crosses indicate alarms for the Kreise. Here you have alarms on the Regierungsbezirk level, and here you have the overall. So you see, for example, here in the overall, if you that means that you take the time series, which happens if you aggregate number of cases in all the counties, then you see you have really this alarm or outbreak part here between 2000 and 2001 in the year, more or less in the year 2000. So this is using the Farrington algorithm, and we do this here on a monthly basis, so 12 months per year. So data here are monthly. Okay. So yes, so one can think about, okay, looking at the time series of the Regierungsbezirk, we still see this. The green crosses here, we see here in the south of Hesse, we have a consistency. That alarm also replicated here in the total. So it was so strong that even once you aggregate with the other 2 Regierungsbezirke, which apparently at that time didn't have any alarms, you still got an alarm. For example, this here in the middle of the middle region of Hesse, they didn't produce an alarm in the overall time series. And you can further drill that down by looking at the individual Kreis alarms, and you really see that the where it originates from is this Kreis here, which is 06435. And then you could, for example, look at some kind of database, which is 06435, and it's the Main-Kinzig Kreis, which is very close to the city of Frankfurt. And you have here also down there the 06412, which at a bit later stage also has an alarm. It's not, doesn't replicate in the big one, but this is one here, which it's the city of Frankfurt, which is a bit unusual, you could say, because that's not where you expect rabies foxes to be detected most often. So this is, I think, if they find a corpse of a fox, it will be sent for testing, and they will try to figure out if there's a rabies positive. That is, there's a reporting demand for this. So if you, and they looked in the year 2000, and they saw that they have this problem here with, in 2000, they also had, I think, this one here, but I'm not 100%. I think it's this one here, 06438. Maybe I should check. It's which is Offenbach, and here this is close to Frankfurt. And what they actually then they started to look at that, and actually sort of like why is rabies? I mean, this is it's a long-standing problem in wild population, and in particular foxes, rabies. So actually, what had been done is that they tried to get rid of the rabies by using vaccination of these foxes. And of course, you can't hunt down every individual fox. So what they did is they dropped bait, which was some kind of polenta filled with vaccine, and then they were hoping for the foxes to eat this because, in particular, they like that. And what happened is actually that they dropped that by airplane over regions, and once they started to detect these, that they had, and this was done over the entire federal state of Hesse, or at least the regions which were previously exposed, and this was one of them. They didn't understand why they had a lot of cases close to here, which is the Main-Kinzig-Kreis, and here this is, I think, sort of city of Frankfurt. Which made them investigate why. I mean, one suspicion was that the vaccination campaign did not work as well as they wanted. So at least that's one investigation. And at least one possible explanation is they came up with is once they looked at the GPS tracks for how the airplane flew. And let me see if I can get that done here. So once they looked at stuff like that, they could see, well, they had some GPS tracks, and of course they looked. I'm exaggerating here, but it looked maybe like this, and maybe on another day, could say they flew something like this. Exaggerating here, and of course, sort of like what the clever one notices, of course, sort of like there was a problem, that there was a region where they didn't fly, where no polenta was dropped, so no vaccine. Of course, this was because of the airport, the big Frankfurt airport. They couldn't fly there. It's a no with a small plane, because you sort of start to interfere with the other big planes coming, so you're not supposed to fly there. And of course, this was not a big operation or something as big so big that they could get an exception for that. So of course, they had a problem that in this area here there was not enough bait dropped for the foxes to be vaccinated. So of course, it ended up that they had a bigger problem there than in other regions. And you could say, well, couldn't they have realized that before? Maybe, but this is something where they really had the advantage of using such surveillance algorithms, because you really detected that in this, at least close in this region, that was a problem, and it was partly related, I guess, to this vaccination distributional problem. So that's one example of that. It's actually monitoring something like this in conjunction with other things, or at least this leads to investigations where you, at least if you look long enough, might find an explanation. Of course, there could also have been other explanations. Maybe part of it is also a bit of a different one, but at least here's one very probable cause. And of course, then they tried to fix that they took different ways of distributing the polenta in these regions where they couldn't fly, maybe drive it out there by truck and just throw it out from the truck instead, or other ways, whatever is feasible there. So this is one example and what we did there is simply we used univariate monitoring for each of them, but still we sort of also use this hierarchical approach because they are geographical regions, they are connected. You can see how that replicates. And one sort of like fair question is, what is actually the best geographical scale to monitor this in? As it would, if we got here, up here, we would have got an alarm. Here we would have also seen an alarm, but where does it originate? Then maybe you want to drill down. So that could be sort of at least one that you always want to click on such an outbreak, see which region is it located to, or is it maybe several regions. And of course, you also, what we did is we always used a different alpha, right? So here we use a lower alpha, because we have more regions, and here we use higher alphas, right, in order to adjust a bit for the multiple testing problem. But this is, of course, just one very simple, maybe, but maybe very intuitive way. So in the second part of the lecture, and this one is first part was rather short, as you probably noticed, but in the second part of the lecture, we will talk about the Kuldorf scan statistics to approach this, and this will take a bit, there's a bit more theory to explain there. So this is what I will be doing in the second part of the lecture, but I'll stop here, give you a small break, and I'll see you back in part 2. And for that, I need to figure out how to